Hello everyone, I am Vaishnavi Bansode from EDA Batch 2 Data Science. Today I'll be explaining a very important concept from machine learning, that is optimization of loss function and the best fit line using gradient descent. This topic lies at the heart of regression and one of the most essential techniques used in predictive analytics and data modeling. Let's start with the first slide. That is the need for optimization in regression. Let's start with the big picture. In regression, we often work with scatter data, raw data points that don't fall exactly on the straight line, but show some general trend. Our goal is to find a best fit line that represents the strain as accurately as possible. This line minimizes the prediction errors and what we call is the residuals. That's the difference between actual observed values and the values predicted by our model. But here's the challenge. No line perfectly fits all the point. We need a way to measure how good or bad our predictions are. That's where the concept of loss function and optimization comes in. Optimization in machine learning simply means we try to adjust our model parameters like slope and intercept so that the prediction errors are as small as possible. So in short, regression gives us relationship between variables and optimization helps us make the relationship as accurate as possible. Moving to the next slide, that is core objective. The core objective here is minimizing the error. We do this in 3 steps. Define the quantifiable error metric, usually the loss function. Identify the optimal parameters. There are usually basically 2 parameters, that is slope and intercept. Iteratively adjust the parameters to reduce the error step by step. Think of it like learning. We make a prediction, measure how wrong it is, and then correct ourselves in step until we get it right. The simple regression model, let's understand it. Now let's look at the simple regression equation that says y equal to mx plus c. Here, y is the predicted output, x is the input feature, m is the slope, and c is the y-intercept. Y-intercept is nothing where the x is equal to 0. Now, the slope m tells us how steep the line is, or in other words, how strongly input x affects the output of y. The intercept c is simply the value of y at x equal to 0. As I said, our task is to find the right m and that make the line best represent the given data, right? The best fitting line. You can imagine you're fitting a line through a bunch of points. You're adjusting the tilt and height until it cuts through the middle of them as clean as possible. So let's go to the next slide. It says defining prediction error, that is the loss function. To evaluate how well our line fits, we calculate how far each predicted value is from the actual observed value, right? This distance is called error or residual. A popular way to combine all these individual errors is the mean squared error, that is MSC, represented as the given equation. Now, yi is the actual value, yi hat is the predicted value, and why do we square the differences? It is because we don't want positive or negative errors to cancel each other out, because as points are as few points are above the line and few points are below the line, since the differences could be therefore the differences could be negative as well. So squaring it gives us a positive answer and we can sum it. There won't be a chance of any error. Now it also penalizes the larger errors more heavily. Now, squaring a number increases its value. Therefore, the larger value of the error, uh, it weighs a lot. ठीक है? Finally, we take the average across the data points, giving us a single number, the loss that measures how bad our predictions are. Lower the loss, better the model. Now let's go to the next slide. Optimization, searching the global minimum. Now comes the optimization step. Finding the value of m and c that minimizes this loss function. Imagine the loss function as a 3D bowl-shaped surface called a cost surface. The bottom of this bowl represents a global minimum or the lowest possible loss. The axes of the surface represent our parameters m and c, and the height represents the loss jmc. Our goal is to reach the lowest point, the sweet spot where the loss is minimal. But instead of guessing, we use an algorithm that can systematically walk down this bowl. And that's what gradient descent algorithm does. Think of a small ball rolling down the slope of a hill. It always moves in the direction of the steepest descent until it settles at the lowest point. The gradient descent algorithm. Let's break down how gradient descent works in simple steps. Initialize the parameter. We start with random guesses for m and c. Calculate the gradient. This means finding how the loss changes when we change m or c. We update the parameters. We adjust m and c in the direction that reduces the loss. And we iterate and converge. We repeat this process until the loss stops decreasing significantly. This iterative process ensures with each step we move closer and closer to the minimum loss. Let's say, for example, imagine our slope m starts at 0 and our first gradient shows increasing m decreases the loss. Then the algorithm adjusts m upwards slightly. If that helps, it keeps going, and if not, it reverses the direction. Eventually, it converges to the perfect balance. Let's understand the parameter update equation. The mathematical update rule for gradient descent looks like m new equal to m old minus alpha jm. Alpha, alpha derivative of j with respect to m. Now, it could also go like if for y-intercept it goes like c new equal to c old minus alpha partial derivative of j with respect to c, right? So a partial derivative of j with respect to m and with respect to c are nothing but the gradients. They tell us how the loss changes with respect to each parameters. Alpha is the learning rate, which controls how big each step is. We subtract the gradient because we want to move downhill on the loss surface. The algorithm keeps adjusting m and c using this equation until the loss becomes as small as possible. Let's understand the learning rate and convergence. Since uh, alpha is nothing but the learning rate, which is the most critical part of the gradient descent. If alpha is too large, the steps we take are huge, right? And if alpha is too small, the steps are tiny. Taking the steps as huge, we might skip over the minimum and the algorithm could start oscillating or diverging. But if we take the step smalls, that are tiny will reach the minimum eventually, but it will take forever. So the learning rate must be carefully tuned, just right to ensure steady and stable convergence. We say the algorithm has converged when the change in loss becomes negligible, the parameter m and c stop changing, and the gradient value approach zero. That's when the algorithm has found its best fit line. Now, moving to the conclusion, we can visualize this as the loss value gradually dropping with each iteration. At the start, the loss is high. After 10 iteration, it reduces significantly, and after 50 iteration, it becomes very small and stabilizes. This flattering of the curve means convergence. The model has learned the best parameter, so the entire process from initial guess to optimal values is like algorithm gradually learning from its mistake. The key application includes in sales forecasting, in neural networks, in healthcare. Anywhere a machine is learning from data, gradient descent is probably running under the hood. So the conclusion, to summarize this all, regression fits a line to data using parameters M and C. The loss function measures how far off our predictions are from reality. Gradient descent is the method we use to tweak the parameters so that the loss is minimized. So every time a machine learning model improves behind the scenes, it's performing some form of gradient descent, stepping carefully downhill to reach the point of least error. Thank you for watching.